Let us check the invariance of Maxwell's field equation in terms of four vectors under Lorentz transformation. The covariance or the invariance of Maxwell's field equations means the set of Maxwell's equations should have same form in any two inertial systems. Let us choose two inertial systems S and S prime. The Maxwell's field equations in terms of electromagnetic potentials A and phi in general are given by del square A is equal to minus mu naught J and del square phi is equal to minus rho by epsilon naught with the Lorentz condition div A plus 1 by c square into dou phi by dou t is equal to 0. Here del is nothing but it is the D'Alembert operator. Now let us write the electromagnetic potentials A and the current vector J in terms of the four vectors. In terms of the four vector, the electromagnetic potential, vector potential is represented by A mu and the current vector is represented by J mu. And A mu has four components in general which is represented as A comma I phi by C, and A stands for the three spatial components A1, A2 and A3 with the fourth spatial component A4 is equal to I phi by C. And the current four vector J mu is represented by J comma I0 with the three spatial components J1, J2, J3 with the fourth component J4 is equal to I0. Now let us write the transformation equations connecting the two inertial systems. These four vectors transform like Lorentz transformation, and the transformation equations are given by A1 prime is equal to A1, A2 prime is equal to A2 and the A3 prime is equal to gamma into A3 minus V phi by C square and phi prime is equal to gamma into phi minus VA3. In the same way, for the current vector, J1 prime is equal to J1, J2 prime is equal to J2 and J3 prime is equal to gamma into J3 minus V rho, rho prime is equal to gamma into rho minus V J3 by C square. And here gamma is equal to 1 by root of 1 minus beta square, where beta is equal to V by C. Now let us write the Maxwell's equation in terms of four vector as del square A mu is equal to minus mu naught by J mu. So with the Lorentz condition, dou A mu by dou x mu is equal to 0. So these two equations 6 and 7 represents the Maxwell's equation with the Lorentz condition in S frame of reference. In the same way we can write it for S prime frame of reference also as del prime square A mu prime is equal to minus mu naught J mu prime. Here this del prime should have a prime sign there which I have missed it here. With the Lorentz condition, dou A mu prime by dou x mu prime is equal to 0. So this equation 6 and 7 and 8 and 9 should be consistent with each other when you grow from one inertial frame of reference to another inertial frame of reference. Now let us check that. So let us take the first component of A mu. So del prime square A1 prime is equal to, this del prime square is equal to, that is the D'Alembert operator. Del prime square is equal to del square which is already proven 1. So it is del square A1 prime is equal to A1. So we know del square A1 is A is equal to minus mu naught J. So here we have wrote it as minus mu naught J1. And J1 is equal to J1 prime. So del prime square A1 prime is equal to minus mu naught J1 prime. In the same way, we can work out for this A2. So it is del prime square A2 prime square is A2 prime is equal to del square A2. So del A is equal to minus mu naught J. So here it is minus mu naught J2. del prime square a2 prime is equal to minus mu naught j2 prime. Now let us quickly check the third equation. Del prime square a3 prime is equal to, so del prime square can be written as del square, and the transformation equation for a3 prime is equal to gamma into a3 minus v5 by c square. So let us bring del square inside, so it is gamma into del square a3 minus v by c square del square 5. We know del square a3 from the first Maxwell's equation, it is minus mu naught j3, so minus v by c square. So del square phi is equal to minus rho by epsilon naught from the Maxwell's second equations. So it is minus gamma into, so a negative sign is present in both the parts, so I am taking it outside. So minus gamma into mu naught j3 minus v rho by c square epsilon naught. We know the square of the velocity of the light is equal to 1 by mu naught epsilon naught. So mu naught can be written as 1 by c square epsilon naught. So in the second term we have c square epsilon naught, 1 by c square epsilon naught, which can very well replaced by mu naught. So replacing it, you get minus gamma into mu naught j3 minus mu naught into v rho. So mu naught is common in both the terms. Let us take it outside. So we get minus mu naught gamma into j3 minus v rho, which is nothing but it is j3 prime. So we got del prime square a3 prime is equal to minus mu naught j3 prime. So we have proved a third transformation equation also. Now let us do the fourth one. Del prime square a4 prime is equal to, so del prime square can be replaced by del square, and the fourth component a4 is nothing but it is I phi prime by c. So the value for phi prime is equal to gamma into phi minus va3, that is the fourth transformation equation for a. So I by c gamma is common for both the terms. We are taking it outside and bringing del square inside. So it is del square phi minus del square va3. Again, we know the value for del square phi from the Maxwell second equation. It is minus rho by epsilon naught. And we are taking the v outside. So it is del square a3 inside. And del square a3 can be very well replaced by minus mu naught j3 from the Maxwell's first equation. A negative, a minus is present in both the terms. Let us take the minus outside. So it is minus I gamma by c into rho by epsilon naught minus v mu naught j3. Now we know c square is equal to 1 by mu naught epsilon naught, or I want to replace it for mu naught. So mu naught is equal to 1 by c square epsilon naught in the second term. So we can see the epsilon naught is present in both the terms and we are taking it outside. So minus I gamma by c epsilon naught into rho minus v j3 by c square. And rho minus v j3 by c square is nothing but it is the fourth current density equation, transformation equation. So we can easily replace it by rho prime. So we got minus I rho prime by c epsilon naught. So 1 by c epsilon naught is nothing but it is mu naught c. Replacing 1 by c epsilon naught as mu naught c, we get minus mu naught ic rho prime. Ic rho prime is nothing but it is j4 prime, that is the fourth component of the current 4 vector. So del prime square a4 prime is equal to minus mu naught j4 prime. So all the 4 equations, transformation equations in terms of a mu and j mu are consistent in both the frames of reference. Now let us quickly check the Lorentz condition also. So we know the equation which transmutes between the a mu and x mu can be very well written as a mu prime is equal to summed over nu a mu nu into a nu, and x mu prime is equal to summed over nu a mu nu into x nu. Hence, dou x mu prime by dou x nu is equal to a mu nu. Therefore, we can write dou a mu prime by dou x mu prime is equal to summed over a mu nu into dou a nu by dou x mu prime. This a mu prime can be replaced by dou x mu prime dou xv into dou a v by dou x mu prime. So in this, dou x mu prime and dou x mu prime gets cancelled. So we are left with dou a mu by dou x nu. Now let us replace the indices nu by mu. So you get dou a mu by dou x mu. If dou a mu by dou x mu is equal to 0, definitely dou a mu prime by dou x mu prime is also equal to 0, which means the Lorentz conditions are also invariant under Lorentz transformation. So this shows, or this proves, that the Maxwell's equations are invariant or covariant under Lorentz transformations.